Okay, thank you, guys. SLE133 tutorial. I'm going to jump the significant figures and move on to some of the mathematics involved. I'm going to do 1.70D. 12.4 milligrams plus 6.378 milligrams plus 2.089 milligrams. So our units here are going to be in milligrams because it's an addition. And if we solve for this, we get 20.867. It's an addition, so we go to the lowest number of significant figures, decimal places, 1, 3 and 3. So the answer needs to have one decimal place. So our answer is 20.9, rounding down rounding up. The next one I'd like to do is 1.71A, where we deal with some unit issues as well as the mathematics. 5280 feet per mile multiplied by 6.2 miles. So this is 1.71A. If we solve for this, we get 32736, and for the units we need to cancel out miles. We're left with feet, remembering that miles is over 1. So it's 32736 feet. For significant figures, because it's multiply, we're interested in the significant figures. We have 2 significant figures here and 3 significant figures here. We need to go to 2 significant figures. We convert this in scientific notation. Times 10 to the 4, because we're moving the decimal place 1, 2, 3, 4. To get that to 2 significant figures, we go to 2 and we actually round up. .3 by 10 to the 4 is our correct answer. Next, I'll do 1.86. This is very similar to 1.89, where we're given the temperature change. So 1.86, we're asked with a certain amount to calculate the specific heat. We're given 96 joules of energy, heats 5.0 grams of our metal from 25 degrees to 75 degrees Celsius. So our specific heat equals our energy, joules, divided by our mass in grams, 5.0, multiplied by the change in temperature. Note that it's 25 to 75 degrees C, so our change in temperature is actually 50 degrees C. Multiply is inferred there. If we solve for this, we get 0.384 joules per gram per degree C. We note that we have 2 significant figures, 2 significant figures and 2 significant figures. It's a divide and multiply, so we must go to 2 significant figures. So it rounds out to 0.38 joules per gram per degree C. So please try 1.89, you'll find that's quite similar. So I'd like to do 1.90, which talks about aspirin having a density of 1.40 grams per cubic centimetre. And we're is the volume of that? So we need common units, so this is one way to solve it. You could also look at other common units. I'm going to convert our grams to milligrams, so I've got a convenient unit. So we're going to use our 250 milligrams. We're happy with those units. We're going to convert this to milligrams, which becomes 1,400 milligrams. You could just as easily convert this to grams and keep that as 1.4. It would be 0.250. Then this is per centimetre cubed. So if we divide 250 by 1400, we get to 0.178, and our answer is in centimetres cubed, our volume that we're after. Why? Because this unit is in the denominator, this flips, and we actually cancel out the milligrams, and we have our centimetres cubed as our numerator there, so that we're in our correct units. 3 significant figures, 3 significant figures, we have 3 significant figures. So the next question I'd like to work on actually jumps forward to chapter 2, where we start to talk about elements. So here we're dealing with our periodic table, and we're asked to describe certain areas that the particular groups come from. So the alkali metals come from group 1. The halogens come from our group 17 or group 7, depending on which way you wish to describe it, but the second last column to the right hand side. The alkaline earth metals are in column 2. The transition metals are the gap between our 2 main group elements, and could include those inner transition metals. Hydrogen is in the top left hand side, and helium is in the top right hand side. Unique elements to know. And our metalloids come, the 6 that are between our metals and non-metals that we've discussed in class previously. So next I'd like to talk about how atoms of different elements differ. Question 2.35. And I'm going to talk about this because of the answers I got in one of the tutorials. So it was mentioned that protons, neutrons and electrons may be significant. However, elements, to be given a known element, if we know what element we have, we must have that number of protons. So it is the proton that tells us the type of element. And so that actually is our answer. Noting that we could have same electron configurations for 2 different elements, and because of what we've already discussed isotopes, it's possible to have the same number of neutrons and still for it to be a different element. So it's the protons that make our elements differ. So I will do 2.36a, which asks, we're given the atomic mass of bismuth, and we're asked to find the mass in grams. So bismuth is 208, which is what we're given, 0.9804. And so we need to associate that, we want to get an association in grams. That's atomic mass units, or U. 1 atomic mass unit weighs 1.660,539, you can find this in the textbook, times 10 to the negative 24 grams. So going from AMU to grams, we multiply it by that, because 1 AMU weighs this much. If we calculate that, we get 3.48606 times 10 to the negative 22 grams. Remember, that's grams per atomic mass unit, so they actually cancel out. So you should be able to trial that for xenon and helium. It's the same approach, we just have a different value here. In each case, we'll be multiplying by this value. Okay, so in 2.37, we're asked 2.37, find the mass in atomic mass units of the following. 1 oxygen atom with a mass of 2.6 by 10 to the 23 grams. So if we have 1 oxygen atom, equals 2.66 by 10 to the negative 23 grams. We want to know what it weighs in atomic mass units, 1 atom. Grams, 2 atomic mass units is the same value that we described before, but now we're going in the other direction, so we must divide by that 1.660539 times 10 to the negative 24. And it's nice to put this one into your calculator to ensure you can get the value. And so in this case, we're dealing with grams per atomic mass unit. They will flip because they're underneath, and our grams will cancel, we'll be left with atomic mass units. If you solve for that, 16.02 AMU, or atomic mass units. This is the value that you'll actually see for 1 oxygen atom in the periodic table, the mass associated in the periodic table. Trial it for bromine and see if you get the same mass that you find in the periodic table, which is part 2 of that question. So next I'll do 2.38. We're asked, what is the mass in grams of 6.022 by 10 to the 23 nitrogen atoms? So we have 6.022 by 10 to the 23, a very large number, very many nitrogen atoms. And we're told that nitrogen has, each one weighs 14, so be careful on this, significant figures, 14.01 atomic mass units. So if we're to solve for this, we're asked to get to what is the mass in grams, so we know that that's going to be our answer. We need to associate that process. So it's just like what we did before of our mass associated with it, 14.01 times our 1.660539 times 10 to the 24. Same step that we decided before. In the last question though, we only had 1 atom. Here we have a very big number. This number is also sometimes called Na, or Avogadro's number, and become important when we deal with moles. This is the number that we use to count molecules. When we count a number of moles, there's this many molecules of interest in that packet, in the same way that when we count number of eggs in a carton, if we say a dozen eggs, we know we have 12. If we have a mole of something, we have 6 by 10 to the 23 of them, very many, a large counting number. So this is just what we did before. Instead of having 1 atom, we have this many, so we multiply it by Avogadro's number, and we'll solve for our answer in grams, which is 14.01 grams. And we'll note, and you can see this for carbon 12 as well, in terms of our basis, atomic mass unit, if we have 1 mole of them, or Avogadro's number of them, you'll see that you have a link to that number. Some of you may have done a shorthand to get into that. So, next we're asked what are the subatomic particles and what are their masses. You can look these up in your textbook. I'm going to talk in a general, so for the exact values, but I'm going to talk in a general sense, which is a convenient way for us to use them. So, neutrons weigh approximately 1 atomic mass unit. Protons weigh approximately 1 atomic mass unit. And electrons weigh approximately 1/12 of an atomic mass unit. We'll often refer to just using 1 for a neutron and proton for adding them up, and we'll tend to often neglect the electron because it's so small. Neutrons are neutral. I'll call that plus and minus together. Protons are positive and electrons are negative. We'll ask for the properties there. Okay, 2.44, give the number of neutrons in each naturally occurring isotope of argon. So, we had argon 38, argon 40, argon 36, argon 38, and argon 40. That's what we're given, and we were asked, give the number of neutrons in each naturally occurring isotope. So, because we've got some information here, extra information, we know the number of protons. The number of protons for argon is 18, and because it is protons define the element, in each case, because they are all argon, there's 18 protons. Our protons plus our neutrons give us our number that we're looking for, our atomic number. So that's going to become 36 in total, 38 in total, and 40 in total. So 18 plus 18 equals 36. So we have 18 neutrons in that example. 18 plus 20 will get us to 38. And 18 plus 22 will get us to 40. You could have also done 40 minus 18, which will get you the same values. 38 minus 18, 36 minus 18. Next, we're asked to give the number of protons, neutrons and electrons in the following isotopes. Aluminium 27, they're written in this specific way. Silicon 28, our boron 11, and a silver Ag 115. Okay. So, in each case we're asked for the number of protons, neutrons and electrons. Because we know the type of element, we know the number of protons. Aluminium, we know where it comes in the periodic table, so it has 13 protons. Silicon, very close to it, has 14 protons. Boron, which is very early in the periodic table, has 5 protons, all from the same source. And our silver has 47. Because of the style of these two numbers, you'll note that we actually had the number of protons listed. A shortcut you could have used. Neutrons, we have 13 protons. We have to get to 27 in total with our neutrons. Becomes 14. 14 needs to get to 28. So again, we have 14 neutrons. Again, noting that we've got different elements, same number of neutrons, it is possible. Boron needs to get to 11, so it's 6. And we've got 47, we need to get 100 to 115 for our silver, so it's 68. Because these are all electronically neutral, we have the same number of electrons as protons. 14, 5, and 47. But note that now we're starting to talk about ions. So sometimes this value will vary. If they do vary, then we've got a charge associated with that element, and it's an ion in that sense. Okay, so our final question is actually listed as 2.52 rather than 2.32, which I think was a typo in the unit guide. So, naturally occurring copper is a mixture of 69.17% copper 63, and that has a mass of 62.93. We have 30% of copper 65 with a mass of 64.93 atomic mass units. We're asked what is the atomic mass of copper. So we need to get that average the average associated from all those isotopes. So I'll call it average. Equals a contribution from the copper 63, which was 69.17% that I've converted to a fraction. That one we were told weighs 62.93 atomic mass units. That's the contribution from that particular isotope. We had 30%, so 0.3083. Again, converting a percentage to a decimal for our copper 65, which actually weighed 64.93. We're rounding up in both cases when we talk about copper 63 and copper 65. So we'll get the contribution from both. There is more of this in terms of proportion, so we'd expect this number to be larger. Let's see how we go. We solve for that, we get 43.52 plus 20.02. Again, if we add those two together, we get 63.54 atomic mass units. And I encourage you to go and see how that compares to the value in your periodic table. Now, consistent with the tutorial that I ran here on Thursday, we didn't go through any significant figures questions. The class was comfortable with that. If you would like more of them, if you'd like me to cover those, I will cover them in future tutorials. Please give me any feedback or ask any questions for future tutorials because of our, I suppose, fast nature of going through in a recording and anything extra that you want covered.